Hello everyone, welcome to the ninth lecture of this course, and in this lecture also we will be looking at numerical computation. So in the last lecture we were introduced to numerical computation, and throughout the last lecture we have learned about interpolation. So in this lecture we will continue learning about the numerical computation. Specifically we will be seeing how to do differentiations. Okay. So we'll first see what is the difference between the traditional way of doing symbolic differentiation and how different numerical approximations can be made to obtain this differentiation of a function or a data set numerically. And we'll be using all the features of Julia to make our life as easy as possible. Okay, so let me quickly tabulate what our goals will be for this lecture. So first, we will look at differences between symbolic and numerical differentiations. We will see how numerical differentiations can be done. We will write a function from scratch. We will do numerical differentiation of functions as well as discrete data points. Then we will also use a package which has all the functions defined. Finally, we will compare the results. And if time permits, we will start numerical integration in today's lecture. If we do not have time, then we'll tackle all about integrations and ODE solving next video. Okay. So this is our goal for today's lecture, and let us visit the presentation that I showed you earlier in the previous class. So today our topic is differentiation. So we all know the basics, right? So here are some formulas that we are all familiar with. That differentiating e to the power x will give you e to the power x. Derivative of sin x is cos x. Then a derivative of a polynomial, say x to the power n, will give you n x to the power n minus 1. Similarly, differentiating log x will give you 1 over x. Okay, so these are all examples of doing differentiation symbolically. We know these formulas, then we use several methods like bypass or substitution to boil down the problem to smaller versions, and we can use these known formulas. There are many more formulas other than these. Our goal in symbol differentiation is to boil down the problem into smaller ones so that we can use our known formulas and get the answer. Okay, so this is how we are used to doing differentiation. That's what we have learned in class 2 and then after that. Okay, so what is the difference between these way of differentiating functions and numerical differentiations? The first thing is that in numerical differentiation we do not have a functional form. What we have is only data. And that is relevant because in real world, every time we're doing experiment, we're collecting data. So the goal is to embrace this and see how we can work with only numbers and how that will help us understand the change of these numbers. Okay. So differentiation, as you know, is basically talks about how fast something is changing. So that will be time derivative. So we can look at those kind of things. Suppose some quantity that you have gathered with respect to time. And if you're differentiating, you will be getting the change in that data, the rate. Okay, so that is the basic differentiation. In symbolic math, we already know the formula and we have some recipe that we're going to be using to tackle any problem at our hand and ultimately use the known formulas. But in numerical differentiations, we cannot use those formulas because only thing that we have is numbers. Although there are some cases, for example, you can do card fitting, you can do some interpolations. Suppose your data is very predictable, and just by plotting it, you can guess a function that will completely match your data. In those cases, you can use these symbolic formulas, but in most of the cases, you will be left with only numbers, and there is no way of knowing what kind of function that numbers are representing. So what you have to do, you have to just take those numbers in our hand and differentiate those. So how to do that? So we will go back to the basics, and before even having this formula, I will just request you to remember the definition of how to find the derivative, and this is given by this, right? So if you have a function f of x, and if you are trying to differentiate it with respect to x at a point x equal to x1, then how can we do that? That will be equal to the ratio of f at x2 minus f at x1 divided by whole thing divided by x2 minus x1. And this will be true only in this limit where x2 minus x1 is infinitesimally small. So this is the formula from which we can get these results, right? So every formula here can be derived from this basic equation. For example, if we are looking at this e to the power x derivative, then we can replace it here e to the power x2 minus e to the power x1, and we can consider that x2 is x1 plus h. Then we can, if h is small, then we can use the formula to approximate that, and from that we can get this formula, and that is true for all of these functions. Okay. So what we will do when we're doing these numerical differentiations, when we're just differentiating numbers, we'll be using this basic formula. Okay. How can we do that? Let us see in the next slide. So suppose we are differentiating discrete data points. So I have just assumed that the function that we have taken is being represented by this y variable. Okay. So what we are calculating is dy dx at a for position x equal to x I minus 1. So why I am using this I variable instead of 1, this is because we are now talking about discrete data points and these are represented in form of an array. Okay. So what is this will give us? We can just write it in terms of delta yi minus delta xi, which will be in turn equal to yi minus yi minus 1 whole divided by xi minus xi minus 1. So these are the differences of the values of y, and these are the differences in the values of x. So when we are differentiating, this boils down to this formula, and this we can use like this. Okay, so we can just use a for loop and calculate this expression over the whole array. So how to interpret this? So suppose this is our x array, this is our y array, and the values are stored like this. So x index 1, this will be x1, at index 2, this will be x2, x3, similarly at up to x7 have shown, and this is y. So when we are calculating this dy dx at say x equal to x2, so at second index, so what we will do, we will take the difference of y2. You can just look at this formula. So at I equal to 2, this will be y2 minus y1, then whole thing divided by x2 minus x1. And that will give us this. Here, when I'm writing this formula, I have carefully omitted the limit, which we all know that is a crucial thing in calculating derivatives. But here I have not shown that, and we will show it in the code that what is the role of this limit. And you will see that when you are doing this differentiation of numbers, we ourselves have to make sure that when we are calculating the derivative, the points that we are taking, for example, this x2 and x1, the difference between them is sufficiently small. And how can we check those things? We will look when we are doing the live coding. Okay. So I suppose I have talked about these numerical differentiations and the theoretical concepts behind it enough. So let us go back to our notebook and see how we can use this in our notebook, and we will write a function again, and we'll try to verify these formulas. Okay. So let us begin. Okay, so let me quickly write these also. We will write a function which we can use to get derivatives of a discrete data set, and we will verify the known symbolic formulas. And let me also write the basic uh, concept that we'll be using. We'll be using this, that dy dx at x equal to x1 is equal to, let me write the limit formula first. Limit h tends to 0. So this will be by h, and so all this will be at x1. Okay, so this is the formula. So let me format this part also. Okay, so you can identify that this is the same formula as this. I have just replaced x2 is equal to. So we can obtain this formula by replacing x2 equal to x1 plus h. Okay, so you can check that this will be just x2 will be x1 plus h minus this fx1, and this will be just by h. Okay, and the limit will be, which is x2 minus x1 is tends to 0, will be just h tends to 0. So you are probably more familiar with this form. And we are saying that this is similar to, so let me copy some part. So this we are saying that we can approximate it by doing this discrete difference calculation. So this is going to be x, this is going to be y. Let's say x equal to x1. So we are saying that this formula can be used like this. And how to calculate the difference? We can simply calculate it using, so this delta y is just y at ith position minus y at I minus yth position. Okay. So here, how can we modify this formula? So suppose we are getting, so let me also call it delta y underscore I. So we are calculating the discrete difference at ith position. So if we are saying that this difference, this derivative is being calculated at x equal to x1, then this will be equal to this. So let me quickly change the nomenclature. So this will be delta y I by delta xi, and this will be calculated at a position x equal to xi. Okay. So the catch is that xi is equal to x1. So that is how we want to implement this numerical differentiation in our code. Okay. So let us write a function now. Okay, so before using this function, let me quickly add the plotting package also, because we want to verify that all of our codes are working perfectly by plotting them. Okay, so let us wait for a few moments so that this installation of this plotting package in this notebook is complete now. So we'll use the GR backend, and let me also specify the size to be 400 by 300. Okay, let me quickly do a dummy plot to check whether everything is working. And I forgot a comma here, and you can see that this is doing the plots correctly. So let me comment that out, and let me also use a different thing. Okay, okay. So everything is working. Now let us write the function. So let's call it differentiation custom, so that this is not overlapping with other functions name. Okay. So what this will take, so first we will write a function to differentiate a function. Okay, so by function here I'm meaning sine, cos, exponential, those kind of functions. So differentiation of function custom, let us call our function that, and this will take one argument, say the name of the function, let us call it f name, the point x where we want to get the derivative of the function, and let's also add this variable lib or say age so that it is uh, similar with this formula that we have used. So what do we have to calculate? We have to calculate this thing. So the value of this derivative will be, let us call this df, that will be the value of this function at x plus h minus the value of the function at x, and whole thing will be divided by h, and we will return the value of df. Okay, so this is our function. Now let us call it. So we want to get the derivative of the function sine at x equal to 0, and say our h, which is the step length, you can call it step, after which the function will be evaluated again and the difference will be taken. Okay, so let us run it. Just see that this is the answer that is being generated by this function, and let me also add a cell here, right, where I'll just write the correct answer. Okay, so what we are getting here is ddx of sin x at x equal to 0. And those who know the simple formulas, that sin x, derivative of sin x is cos x. So the result will be cos x at x equal to 0, or cos 0, which is in turn equal to 1. And this will be here. Okay, so this is the result. So you can see that our expected result was 1, and what we are getting from this function is 0.99998, so which is exceptionally close to the current answer. Okay, so let us again check for another value, say at pi, and we will see that we are getting the, it should have been -1, and we are getting minus 0.9998. So this is close. So now let us check at pi by 2. The expected result is 0. And here we can see that it is 0.005. So, let me keep this here, and let me change the value of this h from 0.01 to 0.1. So what do you think will happen if I run this code with h equal to 0.1? So I will give you a couple of moments to think, and then I will run the code, and you can check whether the answer that you guessed was correct or not. Okay, so if I run it, then you will see that the correct answer, that is 1, and the answer that we are getting now is 0.988. Although this is very close to the correct answer, the accuracy has surely decreased, right? So you will see the difference in the results between two different age values is 0.002. So this difference might not be significant for your case, but for some other cases, it might be significant. So let me check it again for 0.5, and you will see the more this value of h is, the further we are getting from the actual result. So as we have seen in theory also, that this value of h has to be very, very small. So you can see that in action. So let me quickly add a note here. This has to be very, very small. Otherwise, the answer will not be correct. Okay. So let me check this also at a different location. So say for x equal to pi by 2, this can be evaluated with h equal to 0.01, 0.1, and 0.5. So you will see the expected answer is 0 at h equal to 0.01, which is 0.005, then it is 0.05, then it is minus 0.2. So you can see that for this case, the answer becomes bad. Pretty quickly. Okay, so this function is working. Let me add another case, say this, where the value of h is 0.001, which is very small, and you will see that this gives almost a perfect answer. Similarly, here also, this will give almost a perfect answer. So this is 5 into 10 to the power minus 5, which is very close to 0. So one thing we have to keep in mind while using this function is that the value of h that we are taking has to be very, very small. So only then our answers will be matching with the expected result. So now let us do some plots. For example, here we are looking at the sine function. So let us do a plot of the differentiation of sine here using this function. Okay, this. differentiation of function custom function that we have written here. So let me use a begin and end block, and let me first plot our sine function, say from 0 to 4 pi, and you will see that this is our sine function. Let us also label it. Let us also label cos so that we can compare it with our numerically calculated derivative. Okay, so this is the actual derivative, this orange curve, and the red curve is the original function that we're working with. So let me also use some transparency. Okay, so now we want to use this range, and we want to plot this function on sine on this range, and let's say our age is 0.01. So if you run, this will not work because here we have written this function assuming that this will be accepting a single value, but you can check that this is a range, so you can use the dot syntax, and then this will work, but I have to use it with plot exclamation. Now let me run it, and you will see that this cos plot and this y3, which is this one. So let me add a label also. You can see that these two are perfectly overlapping because you cannot see those two curves separately, right? So what will happen if I make this 0.1? Then you will see that you can see two curves here very slightly. So the difference is small, but the curves are almost following the same trend. Similarly, you can make it 0.5, and then you will see that this green curve, which is the numerically computed derivative, and the blue orange, sorry, the orange one, which is this actual derivative plot, are quite different. So this is again, I want to stress that when you are using this function and finding derivative, you have to make sure that the value of your h is reasonably small. So here you can see that this is almost matching. So that's how you can calculate the derivative of the sine function, and this is matching with our expected result. So let us check this for few other cases. So suppose you want to calculate derivative of cos, and that will be minus sign. And let me remove this numerical derivative for now, and let us plot it. Okay, so we have to specify it like this. So this is the expected result, and let us plot the numerical differentiation also. You will see that again the expected result is completely matching with our numerical differentiation. So let us check another case. Say for example, sine 2x. So let me comment it out for now. So this is okay. This should give you the plot of sine 2x, I think. Yeah, this will give you the plot of sine 2x, and the derivative is going to be 2 cos 2x, right? So let me also plot that. So you can see that this is our actual derivative. Now let us do the numerical differentiation, and here I have to specify the function in such a way that this is just the name of the function. This just becomes the name of the function, and we can do that using anonymous function definition. So we can write it like this. So here we are just trying to write sine 2x. So here we'll be writing it like this. So our function will take one argument, and this will return sine of that multiplied by 2. So it will not be 2 sin x, it will be sine 2x. Okay. So for example, we can check this differently here also. We just check that this is working. So this should be our sine x, and this should be our sine 2x. So this is working. So here we can omit the extra brackets. This is also not needed. This is also not needed. So now you can see that the numerical derivative is again matching with the actual derivative. Let me comment it out. You can see that this faded yellowish orange is the actual derivative, and that if I uncomment it and run it, you will see that it is matching with the actual derivative. So far we have only used the sinusoidal functions, and we have checked that our derivative finding function is working perfectly. Let us look at another example here. So let us run it from 0 to 10, and the function that we're going to be using is exponential. And we can remove this part. So this is our exponential function, and we all know that the derivative of exponential function will be exponential of x. So I just have to change the limit, and you will see that the function and the numerical derivative is perfectly matching. Let us again check another case. So now we will check the derivative of exponential 2x, and the result will be 2 e to the power 2x. So and What's the issue here? Okay, I have to use this dot syntax here and here also. I have added double dot here. Yeah. So you can see that this is our plot. This is the exponential 2x function, and this yellow one is the derivative, which is 2 into exponential 2x. Okay. So now let us check it numerically. So again, you have to pass the anonymous function. This will take one variable x, and this will return e to the power 2x. You will see again the numerical derivative is exactly matching with the theoretically calculated one. We can plot this curve in log scale also. And let me remove the legend. Okay. So you can see that we are plotting this function in the log scale. So the y scale is in log scale. So e to the power x, if you are taking log scale, this is just gonna be a straight line. So this is our actual data, which is straight line, and this is our derivative. So the derivative is 2 exponential 2x. If you take logarithm of that, this will be log 2 plus log of exponential 2x. That will be log 2 plus 2x. So this is our actual data, which is 2x, and this is 2 plus 2x. So everything is shifted by 2. Sorry, log 2. Okay. So you can see that this is working for this case also. So the final check that we will do is for polynomial functions. So say we have this function, say x to the power 5, x to the power 5, and we don't need to plot it in log scale. And let me just see if the plot is working. Yeah. So now let me plot the actual derivative, which will be 5x to the power 4. So this will be our actual derivative. So let us now calculate it numerically. So the function is going to be x to the power 5, and you can see again that the derivative is matching exactly at every point. Okay. So I think these all examples are enough to convince you that this method of finding derivative numerically is working exceptionally well for all the functions that we have seen so far. Now, let us use another property of derivative that we already know, that is superpositions, which implies that derivative of, so let me write it in LaTeX, ddx of y1, which is one function of x, and y2 will be equal to the summation of individual derivative of these functions. Okay, so the dx of y1 plus y2 will be the dx of y1 plus dx of y2. So this again holds true for this numerical differentiation function also. So what we can do is, suppose we want to find derivative of a function, say x squared plus x plus 3. So let us plot it, x squared, sorry, squared plus x plus 3. So let me call it function, let me call it derivative, say actual derivative, and the bottom one will be numerical derivative. So the value of this derivative will be to the power x square, so it will be 2x plus 1, right? So let me plot it, and sorry, this is 2x. So you can see that this is a quadratic curve and this is a straight line. Now we can check whether this equation holds true using numerical derivative approach also. So for the first case, our function will be x squared plus x plus 2. Sorry, it was 3. Again, doesn't matter because this is just a constant. But anyway, let me write it accurately. And you see that it is matching. Now, what you can do also is that you can generate the derivatives of this function separately and add them up. So how can you do that? So the first function is going to be this x squared. Then, so let me write everything in new lines. Then we'll find the derivative of x, and then we'll find the derivative of 3. So, and what we'll do is we'll add all of them. Okay. So what this 3 differentiation function is doing is that this is calculating the derivatives of each of these functions. So it will first calculate the derivative of x squared, then it will calculate the derivative of x, and then it's going to calculate the derivative of these 3. And then you will add all of them individually. And if this superposition theory is correct, what we are going to have is the derivative of this. So if we're plotting both of them on the same plot, they should coincide with this plot perfectly. So let me plot it. Let us wait for a second. And you can see here that our actual derivative, numerical derivative, and the second numerical derivative both are overlapping on top of each other here. So superposition also works in numerical differentiations. Okay, so I think I have check all of this example, and I will keep this one for you guys to check as a homework assignment. Okay, so that is the basics of doing numerical differentiations. Now, let us see what we can do more with this kind of function. Okay, so let me create another code block here. Sorry, this markdown block here. So the first question that one should answer after finding derivative is how to get higher order derivatives. Okay, so that's what we're going to learn. Okay, so before seeing how we can get these higher order derivatives, let me rewrite this function in a different way. Okay, that will actually help us obtaining these higher order derivatives in a easier way. So this was our earlier function. So let me change the name of the function. So what this function is doing is this is taking a function, the point where the function has to be evaluated, and this is returning the value of the derivative of the function at that point. So when we are to get higher order derivatives, what we can do is we can give the values. So let me annotate this first. Earlier was taking a function to differentiate that function. So now this method will work for pure data also. So what do I mean by pure data? Suppose you have collected your both independent and dependent variable in a array. So earlier our data was, suppose, 1 to 10 and sign of 1 to 10. So this was our x or independent values, and this was our y values. So instead of passing these y values directly to the function, what we are doing was we are passing the function only. And then the earlier function was then giving us the derivative of this function at a given value. And it was doing that by evaluating the function at that value plus h minus the value of that function at the given value, and it was dividing the whole thing by this h parameter. Okay, so now what we'll try to do is we will generate derivative from both these x values and y values. So we can use this method to get derivatives when both the independent as well as dependent variables are obtained as data. So that means we do not have any functional form or known expression of the y variable. We only have data. Okay, so as we can see that if we do not have a functional form or known expression available to us for the uh, dependent variable, then clearly the earlier method that we were using will not work, because here this f name was a function, and this custom function was evaluating the value of our dependent variable using this function. But if we do not know what the function is, then we cannot do that, right? So this method, the second function that I will write, that can work on both these cases. Okay, so let me write that y is data and x is also data. So what I want to do here, I want to return an array here, because y and x both are data. So let me also specify that these are arrays, and I will work on both of these arrays, and I will try to return the array here, which will be associated with the variable, say, dy dx, and we will store the derivative in this variable. Okay, so how can we do that? Let us go back to the formulas that we wrote. So here, this function was written with this formula in mind, but we can use this formula also. This dy dx evaluated at x equal to x1 can be written as delta yi by delta xi, where this is evaluated at x equal to xi, and given that xi has the value of x1. So we can write it like that, where delta yi was also defined as yi minus yi minus 1. Similarly, delta x is also defined. So we will use this formula to get our derivative. So how can we do that? We can use a for loop. So here another check that we want to do is that x and y are of same size. Otherwise, the loop will not run. So let me also create this array. So the instantaneous value will be dy dx underscore I, and that will be equal to delta y by delta x. And what was delta y? This was y at I minus y at I minus 1. And the whole thing was divided with the dependent variable, which is x. So delta x will be xi minus xi minus 1. Now we want to append this value into this array. We can do that like this, and then we can return. Sorry, here you have to specify one end to signify that the code inside for block is complete, and we will return the dx dy array. Okay, let me comment this out, and let's make one data set. Say our x1 is 0 to 4 pi, and our y1 is sine of that. Let me first plot x1 to y1, and we can see that this is a sine curve. Now, what we want to do is we want to verify this that this function is working like this earlier function also. Okay, so what can I do? We can check it by plotting them on top of one another. So let me just plot this and use this function, and also give it a label. Let's call it derivative method 1, and we have forgotten a dot here. And if we plot both of them together, you will see that one is a sine curve and another is a cos curve, as we expected. So now what we want to see is whether this function is also giving us the same result as this function. Then we can be sure that both of these methods are similar and they are working similarly. So let us check if all these methods are generating the same results, and then we'll proceed further with this function and we'll see how we can do higher order derivative also. So let me plot the result from this function also. So we'll pass x1 and y1, and I will also pass it a label of derivative method 2, and let us plot, and we will see that this is actually matching with the original function. So here, instead of plotting just y1, we wanted to plot this function. So let me just copy it from here, and we'll pass y1 and x1, and we will see that we are met with an error. So I will pause this recording here for a couple of moments, and I will let you guys figure out where this code is wrong. So there is a very subtle mistake here, and I hope that you will be able to find the mistake. So look carefully in this for loop. So I'll give you a moment to see this and find the mistake, and then I will rectify it and we will do the plot again. Okay. Okay, so I'm back. I hope you have found the mistake. So the mistake here is that if you look at the error message, this will be a bounds error. That means we are attempting to get an element which is not possible, which is not present here. Okay, so what is happening here is that when you are running this loop, the first value of this I variable is 1. So when you are calculating the first element, what this will do is this will give you this y1 element, and this will give you this y0 element. Now, if you remember that in Julia, the array are indexed from 1 up to the number of elements. So the error that we're getting here is that this y I minus 1, which will be y0 in case of I equal to 1, is not present. So in this particular case, we are trying to get an element from an array which is invalid. That's why we are getting this bounds error. So this is I attempt to access 126 element at index equal to 0. So this is the error. So how can you fix it? That's the second question. So we can fix it in two ways. So what we can do is we can write. So let me just comment this out for reference that this will not work. And what we can do is that we can just say that the loop will start from 2, not from 1. So what will happen then? You will see that this is still giving you an error, but a different error. So I'll talk about that later. So now let us look at the execution of this loop. So the first value that this I will take will be 2. So the first value of this dy dx underscore I will be equal to y2 minus y1 by x2 minus x1. So all the values that are being referenced in this expression are valid, and then we can calculate this, and then we can also append this in the array. Now, when in the next loop, when this value of I is going to be 3, then this dy dx I will be y3 minus y2 whole thing divided by x3 minus x2. So you can clearly see that it is going like this. But in the earlier case, the problem was that we were trying to reference an element which is syntactically wrong in Julia. So that is one way of fixing this. Similarly, we can also do it like this. So say we will not start from 2 but from 1, but we'll go up to one last element. And then we have to modify these i's as I plus 1 and these I minus 1s as simple i's. And then also it will not work. So let me comment it out. Then also it will not work. So here, what is the execution of this loop? So first, the value I will take is 1, then dy dx I will be y1 plus 1, this will be y2 minus y1 on by x2 minus x1. And the last value it is going to take will be the length minus 1. So suppose our x array has, and x and y both array has 10 elements, then this loop will be 1 is to 9 or 1 to 9. So this will be at the last iteration, this will be y of 9 plus 1, 10. So y of 10 minus y9 whole divided by x of 10 minus x9, right? So these two will actually give you same result. So the error which was that we were addressing one element wrongly, has been tackled here. But there is another issue. You will see that the code is still not running. So we can run this and go to here, and you can also run this, and you will see that it will still give you an error. So to understand that, let me print the result of this here, and you will see that this is the result. So let us get the length of this, and let us also get the length of x1, and you will see that these two arrays are different in length now. Why is this happening? This is happening because here we are referencing this array up to length of y minus 1. So what is happening? If our array has 10 elements, this for loop will only run for 9 times. So when we are initializing this with an empty array and adding each element in one of the iteration of this for loop, we are only adding 9 elements because this for loop is running according to this range, which is from 1 to length of y minus 1. So we are adding one less element to our array. So that is why there is a one element mismatch in the return value of this function and the x1 or y1 array. So how to tackle that? So remember this formula again. So when we are calculating this xi, then we are looking at xi, xi minus 1, these two elements. So what we have to do is we have to get rid of one of the elements in this array, in our x1 array. So when we are plotting this here, we are giving it one extra element. We have to give it one less element, and that we can do just simply writing this. So this will index from the array starting from the second position up to end. Now if we run it, you will see that all the results are getting plotted. This is still following the derivative one method very closely, but there is a slight mismatch. So why is the slight mismatch happening? We know the answer. This is happening because in this function, we're not specifying the difference between these elements explicitly like we were doing in the previous function. So if you want to calculate the difference, we can check it like this. So the difference is 0.1, and we already know that we have to make this difference as small as possible in order to get this value, the derivative, as accurately as possible. Okay. So what we can do here is that we can make this difference, which is being specified here, as 0.01, and you will see that both the plots are matching. You can also make all of the same, and you will see that both the plots are on top of one another. Okay, so this is how you can also use this function to get derivative of just numerical data. Now, one thing you have to keep in mind that if your data point spacing is regular, then also you need to make sure that each spacing is adequately small. Okay, now we will check this function for a few other numerical datas. But before doing that, let me comment on this. So here the returned array will have one less element compared to the input arrays. So we can plot like this. But should we get rid of the first element or the last element? So that is the question. So here when we are plotting, we are getting rid of the first element. If you look at this for loop carefully, you will see that in the first iteration, what we're doing is we are calculating y2 minus y1 whole divided by x2 minus x1, right? So this is associated with the point x1. If we look at this definition here, you will see that for x1, we are defining it like this. We can also compare it with this. So we are calculating this four derivatives. So x for x1 will be addressing x1 plus h, where h is positive here, right? So in this case, since our x is obtained in such a way that this is numerically increasing, so this here is associated with x1. Similarly, if you want to find what will be associated with x end, we can check and start from this one, and we can rewrite this as this, right? But you will see that this is actually giving you an error. Why? Because this n plus 1 element does not exist for either of this y or x array. So this does not exist for our array. So technically here the element associated with xend does not exist. That means we have to get rid of the last value on x. Okay, so the answer is last value, and here then this will be written like from 1 to n minus 1. So I will, okay, let me just make this smaller so that it runs faster. Okay, so let me quickly go over this once again so that it becomes completely clear to you guys. So we have two different ways of calculating derivatives. The way written here is called forward derivatives, and similarly we'll have backward derivatives also. So this is similarly we'll have backward derivative also. So only difference here is that this will be minus h, okay, and if we translate this to this formula, so this is again the forward method, and the backward derivative will be. So let me just correct it a bit. So this is going to be like this, and yeah, so this is the correct. So this is the forward method and this is the backward method. What is the difference in the forward method? The difference at ith position is calculated with respect to the I plus 1th element, and the difference in the ith element position is calculated with the I minus 1th element in the case of backward differentiation. So what we are implementing in our code here is this forward method. And you will see that when we are trying to get the element after I, so in the I plus 1 position, so if you are doing it like this, you will see that for the end value, we need to address the array element at the position end plus 1, and that is not possible. So in that case, this delta value at the end position will not be possible. So our derivative at the end position will not be possible. So in this function, we have to plot it with x1, 1 to n minus 1. Okay. So this is for forward difference. If we are calculating the backward difference, then we need to plot it with x2 to n. So in order to remove all ambiguity, what we can do is we can return the independent values also like this. Okay. So let me modify this function and let me call it dy dx1, and let me plot this two. Okay. And there is an error, cannot convert to 64 to series data for plotting. Okay, sorry, I forgot to save this. There was an error, cyclic references. Let me quickly return a copy of this. Sorry, we don't need this copy. Rather, we want this to be x, not x1. So now it should work. Let me delete this one and let me go back to our plot. And you will see that this is plotting as we wanted. So let me remove this also. Okay. So now let us check that this is working for two more cases. So let us do for this exponential 2x function. Let me call everything x2 and y2. Okay, so let us plot the derivative of this also. So this is x2, this is dy dx2, this will be also y2, x2, and this and this. And you see that this is the derivative. Now we can also check it visually with this, or we can also copy this from here. Sorry, not here. I need to copy it in the bottom cell. Derivative method 1. And you will see that again, this is working as expected. So our this definition of getting forward derivatives is fine. And now what we see is how we can calculate the higher order derivatives using this function. Okay, so before doing that, let me start with the polynomial function. Let me plot its derivative first, then we'll plot the derivative of derivative. So let me call everything 3. So this was only 3, this will be 2, this is just, this will be the first order derivative. So let our function be x cube. Okay, so let me plot it, and it says that x is not defined. Where? Okay, sorry, this will be x3. And you can see that this is, okay, so let me call it x cube. Okay, so you can see that this is our x cube function, and this is the derivative, which is 3x square. So let me plot that also. And again, this is going to be x3. And you will see that again the yellow and green plots are overlapped on top of one another. So our derivative method is 1. Now, what will be the derivative of this? Let me plot that also. So this is going to be 6x, right? So this was up to, so let me change the limit a bit. So yeah, this was up to 125, and then this was 3x square, and this is up to 6x. So this will be around 30, and you can check that this is having a value almost at 30. So now, if you want to do second order derivative, what we can do is we can use this function again on these inputs. Okay, so the output of your first order derivatives will be used as the input of your second order derivative. Okay, so what do I mean by that? Let me just copy them and let me change the name of the variables. So what we'll do is so the x and dy dx that we obtained by using this function for the first time, if we pass them as an input in the same function for a second time, then essentially what we'll be doing is we will be taking a derivative of this dy dx data, and that will actually give us the second order derivative. So let me plot it. So let me call it second order derivative, and this is going to be div2, and this is going to be dy dx3 underscore 2. And there is some problem. Let me quickly check it. This is saying 3 underscore 2 is not defined. Okay, actually this is going to be same as this, right? So let me run it again. We are getting an error. H3 for D2 again. Sorry, this will be okay. So let me reiterate again. The input for this function when we are calculating the second order derivative will actually be the output of the same function when we were calculating the first order derivative. So this is second order and this is first order. When I was just copying this, I forgot to remove this underscore 2 in for both the values. Now this should work. And you can see that this y3 curve and the second order derivative curve both are on top of one another. So our second order derivative is also working. Similarly, we can create a third order derivative with the outputs of this expression, which is calculating the second order derivative. So what will be the inputs here? This will be dy dx3 underscore 2 and sc for div underscore 2. So let me also plot it. And if you can do simple math, you will know that the derivative of this function, which is 6x, is going to be a constant 6, and you will see that the third order derivative that we have plotted is a flat horizontal line. We can also check that using this hlines command and plotting a line at 6. Sorry, this is h line, and you will see that the let me also give it a label. So 6. So you will see that the third order derivative and this horizontal line at x with y equal to 6 is matching. So you can see that how we can use a simple function here, and we can extend it like this to calculate higher order derivative. Now what I will do is I will introduce you to one of the functions in Julia called the diff function, and we will see how we can use this diff function to write this code in a crisp way, and we can also implement what order of derivative we have to calculate with this y and x data. Okay, so the function that I want to use is called diff. So you can check in the live talk. So this will give you the finite difference on a vector, and it can work on multi-dimensional arrays also. So for this lecture, we are only looking at 1D data. So what we can do is we can give this function this diff, and it will give you the difference. Okay, so it works on multi-dimensional also. So if you want, you can extend all of this code for 2D derivatives. So let us see this diff function in action. So let's first define this x. Okay, this is not defined. So let's say this 1 to 10. So if we run diff of x, you will see that you will get an array which is all 1. So what this function is doing is this is giving you difference between consecutive elements. Okay, so the first value here is the difference between. So let me also call it collect so that we can look at the values. So the first value here, the first one is signifying that this is the difference between 2 and 1. Then this is then for the second index, this will be 3 minus 2, then it will be 4 minus 3, then it will be 5 minus 4, like that. And since again we are calculating forward difference, we will have one less element. Okay, so we can use this simple function in our code, and we can just write dy dx as diff of y, and we want to divide everything element wise. So this will be dot slash then diff of x. And if you just check with this, whether the output of these two functions are equal, we see that this is true. So these two functions are defined differently, but these are giving the same result. Okay, so suppose we want to modify our function in such a way that this will give us the nth order derivative. So let us give another argument to our function, and let us also give it a default value. So when we are just passing y and x, this will calculate the first order derivative. But if we are passing another number which has to be of int 64 data type, this should be an integer, should not be a float. And what will happen is that this will calculate that order derivative. So if we pass yx and 2, then it will give us a second order derivative. How can we do that? Very simple. We can reuse this code over and over. So let us just say that this will be y, and we will run this for this many times, and instead of returning dy dx, we'll be returning y, and this will be n minus n, because for each derivative we'll be losing the last element of the array. So when we're calculating the first order derivative, we will be getting one less element. Then when we're calculating the second order derivative, then we'll be getting one less element from the first order derivative. So in total, we will be losing the last two x points. Okay, so just remember this as a rule. If you are calculating another derivative, then you will not be able to get the derivative of your last endpoints. Okay, so now if I run this, will this work? You'll see that this is working, but if I want to check whether the second order derivatives are equal, we can do it from here, and we can pass n equal to 2, and you'll see that this is giving you an error. So the error here is that I have misspelled this, and now you will get the actual error that I wanted to show you. This will give you a dimension mismatch. So what is happening here is that when we are running this loop, after the first iteration, the dimension of y has decreased by 1, but we are not decreasing the dimension of x. So what can we do? We can simply write it like this. Okay. So what this will do is that when you are doing the first iteration, which is calculating the first order derivative, then this will run from first element to end minus 1 plus 1. That means first to last element. But when we are doing the second order iteration, then I will be 2, then it will be running from first to n minus 2 plus 1, that is n minus 1 elements. So the return that I was doing here can be simulated simply like this. Okay. Now, if we run it, you will see that we're still getting a dimension mismatch. Let me quickly see why that is. So let me just print I and length of y and length of this. So this is clearly, you can check that we are decomposition with an array of 500 elements and an array of 419 elements. So this is clearly off by one error. So let us quickly check. Okay, so I have made a small mistake here. This should not be n minus n, rather it should be n minus I. So now you can check that for the first case, this is calculating for all the elements. So this will be 1 to end only because minus 1 and plus 1 get cancelled. Then for the second iteration, when I is equal to 2, this is going to be minus 2 plus 1, that means n minus 1. And now if we run it, you'll see that there are no errors. So let me quickly delete the empty cells and also suppress this print message. And you'll see that the second order derivative is not matching. So what we can do is we can just quickly plot them. So let me just plot them here only. So let me just remove the third order derivatives, then we can plot this with y3 and x3 with n equal to 2, and let's give it a label, say custom 3, and we can just expand this, and we see that it is matching, right? You can check here that this deep blue and this violet plot both are overlapping. So just to see it clearly, you can see that it was here and these are overlapping here. So the result is correct, but this is giving false for some reason. So let us check it. So let us print this, and let us also print dx 3 underscore 2, and this also seems correct. So whether this is equal to the second element that is being returned, that is true. So you can print all of these return values in this, and that x3 for the underscore 2 function. Okay, this was just a error by in defining the tuple. So what this was doing is it was printing this, and then it was comparing whether this is true. So you have to, if we just make it a tuple and then run, then you will see that this is also returning true. So let me delete everything up to here. Okay, so let me quickly go over all the things that we have done, and then we will look at a package that is written in Julia, which can help us in running this kind of operations. We can do multi-dimensional derivative in that package also. Okay, so let us see from the start. So our goal in today's lecture was to do numerical differentiations, and we have seen what the difference of that is with symbolic differentiations, and we have also checked the basic formula which one can use to get derivatives at a particular point. We have learned about forward method and also the backward derivative method. We have also seen that how we can use that to translate to a case where which only has numbers. So this forward method and this forward method are equivalent, and this backward and this backward method are equivalent. So using that, we have written a simple function which can get this forward derivative given that we know a functional form of which we want to calculate the derivative. If we do not know that function, then for that case, we have also written another function which will work only with data. So we have also seen that these two are giving the derivative correctly, and we have also plotted them together and checked that the results are same. We have looked at another case that when we are getting derivative like this or using the next function, how the choice of this h value is changing the value of the derivatives, and this is actually coming from this case that limit h tends to 0, or the difference in these values of x when you are having discrete data has to be as small as possible. Okay, so we have seen how that works, and at the end we have also seen another function in Julia called this diff function, and we have rewritten these large function here in a compact way here. And we have also seen how to calculate higher order derivatives. So we have checked that using this function as well as this compact function. And we have written this function in such a way that it can technically create any order of derivative. Okay. So with that, let us see a package which goes by the name zygote.zell, and this will help us do this differentiation, numerical differentiation operations simply by using the functions that is written inside of this package. Okay. Okay, so let us go to the GitHub page of this package and also let us look at the documentation. So this is the package zygote.zl, and if you look at the documentation, you can see that this is a package which extends the Julia language to support differentiable programming. With this package, you can write any kind of Julia code, and it will allow you to take a gradient of your code. Okay, so this can be used with existing Julia packages. You can use it with your own functions. You can use it in deep learning, machine learning, probabilistic programming, on all the cases that you might want to use it. Okay. So this can be used like this. We can skip it because we will be using it in Pluto. So how can this package be used to calculate gradients or derivatives? So you can look at this example. So the primary function that you want to use is called gradient, and this will calculate the derivative. For example, if you want to calculate the derivative of this function, which will be evaluated at x equal to 5, the derivative of this is going to be 6x plus 2, and you'll see that when we run this gradient method with this function at x equal to 5, we'll get the result 32. So it is very simple to use it on our function. Okay. So let us see this package in action. So we will start using it with the code using Zygote, and let us wait for our notebook to install this package. This package and the function that it provides has capability of doing these multi-variable differentiations also. This can work on different type of array elements, structs and custom data types. This can work on custom function which uses recursion or break or those kind of statements. So many examples are given here, but in today's lecture, we are only going to look at these functions that we have looked at so far, and we will try to get the derivative of those functions using the gradient method provided by this package. Okay, so let us wait till this is installed. Okay, so this is done. So this will give us a method gradient, and you will see that this has only one method. So how can we use it? We can call this function gradient, give it a function of which you want to get the derivative, and then we can provide at which point you want to generate the derivative. So the derivative of sine at 0, you will see that it is giving us a value to be 1. Similarly, we can look at the derivative at pi by 2, and you can see that this is 0. So 6.1 divided by 70. So you can see that here we don't have to worry about the efficiency or accuracy of the value. We do not have to worry that the data points that we are giving is sufficiently spaced or not. Okay, so this function is intelligent enough to figure it out by itself. Let us look at x square, and let us evaluate it at 2. So this is 0.4. Okay, we have to provide a function, not the expression, so we can make it an anonymous function. And you'll see the result is 4. So can this work on arrays? So let us see that. Suppose we want to do it for 1 to 10. If we run it, it will surely give an error because we have to specify the drop syntax here. And you can see that with cross-clustering enabled, this is evaluating the derivatives at each of these points perfectly. So now let us plot them. So let me first plot, or we can simply use the square function. Let us just use this anonymous method. And then we'll also plot the derivative. Okay, so let me give it a label that this is the function and this is derivative. And it is showing an error. Let me quickly check it. Okay, so if you look at the output of this, you will see that this is giving each point as a tuple, right? So what we can do is that we can use this first function. So let me look at the live talk for a moment. So what this will do is that it will give you the first element of an iterable collection. So if your gradient has, let me run it. So if the result of this expression is array of tuples where the tuple only contains one element, so then if we just run it through the first function, it will just look at each of the element of this array, and when that is a collection, it will only give you the first element of that collection. So if you run it, you will see that this has converted this array in this form. Okay, so we can just copy it and paste it, and let us plot. So let us wait for a moment, and you will see that this is the result. So let me do it for 1 to 5, and let me make this uh, scatter plot just for some visual clarity. Okay, sorry, I have to change the limit here also. One thing you must have noticed that the execution speed of this function is much slower to the function that we have written. This is happening because you see, okay, first let us see that this is the result, and the execution is slow because this is doing much more checking when this is returning the value, and you see the accuracy here is very good. So if we use our function to get this gradient, we will get the answers like 1.99, 4 by 3.998 like that, but here the answers will be completely accurate. Okay, in order to get this accurate answer, this is taking a bit more time in execution. So let us quickly check a couple more functions. We can do this sin x, sin 2x, and exponential 2x, and we'll see that whether the results that we get are predicted. Then we will close today's lecture. We are already over 2 hours, but let us see this for the sake of completion. Okay, so let me first do sine, and let me do it from 0 to 2 pi, and let me plot it. You'll see that this is the result. If we increase the number of data points, you will see that this is our sine curve and this is our cos curve. Okay, now let us check it for exponential. You will see that both the derivative and the functions are overlapping, so this is correct. Let me just do exponential to the power 2x, and you will see that this is the result. Similarly, let me also do sine 2x, and you will see that the result is matching with what we are expecting. Okay, so you can use this gradient function from this scikit-learn package, and this will give you the result that we obtained from the basic principles by writing the functions on our own. Okay, so with that out of the way, let me conclude today's lecture by showing you a simple thing here. So this gradient function is also capable of doing partial derivatives. So what you can do is you can pass it a function which takes two variables, say x and y, and the function is extra y. Okay. So now I want to evaluate this function at say 1 and 2. So if we run the gradient, we see that you will get the answer 2, 1. And this is actually correct because you can check that the partial derivative of, so let me run it first. Yeah, of dx on the function xy is gonna be y. So if we are evaluating it at this point, 1, 0, so let me also write this. If you are evaluating at this point, then the answer is gonna be y here, which is equal to 2, right? So you see that the first thing that it has returned is 2, which is the answer with respect to the first argument. Similarly, we can also calculate it with respect to y, and in that case, it's gonna be x, and the answer will be 1. So this gradient function has capability of evaluating partial derivative also. So I want you guys to look at the different examples of this gradient function and see whether you can do partial derivatives and do some surface plots. Okay, so consider that as a homework assignment. And if you have any questions so far about numerical computation or uh, all the classes, I will ask you again to let me know. So let us conclude today's section with this code block. So what we have learned, so we did numerical computation, mainly differentiations. We wrote some functions from scratch. We plotted and checked that the results are matching with our expected results. We also used the package zygote.zl, which gives us a gradient function which can perform these derivatives. We also checked the importance of difference, the h parameter when calculating derivatives. Okay, So that's what we have done in this class. And in the next class, we'll be doing integrations, and I will solve one ordinary differential equation using this integration method that we will see. Okay, the next class is going to be our last class, and I will try to cover as much content as possible. So numerical integrations can be done with a lot of algorithms. Okay, there are different techniques available for different kind of functions and different kind of use cases, but it will not be possible to cover all of them in one single lecture. So what I will do is I will cover the very basic case, which is Euler forward integration method, and we will see some example problems which can be solved using that. Okay, so with that, let me conclude today's lecture here, and I will see you all in the next lecture.